All right, so, sorry about that. So this, out of habit, I keep wanting to say force. The flux, the luminous flux, this is the luminous flux that's actually hitting a particular area here. So I'm going to sort of define two different luminous fluxes, because there's the amount that's just sort of given off, and then there's the amount that's actually incident upon a particular area. So the incident, the part that hits, is just equal to the total, and then sort of the fraction of the area that actually hits. So area over area of the sphere. Still going down the right path here.
So the F total is multiplied by the area, divided by 4.
Yeah.
Times the area divided by
Still,
4
there's still an issue we're having here. What is the
radius squared.
nice? That over that. Yeah, all that's good.
That's how I felt on my last master set.
Yeah.
There's something wrong.
No, I just have to remember these feelings when I'm writing tests. All right. So therefore, my illuminance would be that total times the area over 4 pi r squared divided by the area that's actually hitting. And we end up with this total, F total over 4 pi r squared. What this is saying is that for a light source that's giving off all this energy within the visible spectrum, if I start pulling my sensor back, my illuminance should be inversely proportional to the distance squared. So that if I have my source here, my light bulb here, and I have a sensor of a set size, that, we'll just say the distance there is R. If I went to twice that distance, my illuminance should be 1/4 of what I had the first time. Because if I double the distance, since I'm squaring it, I'm multiplying it by a factor of 4. And so, even though the angle is getting smaller, that's taken into account. And this is based upon the light bulb. You plug it in, it shines bright. So we don't have to keep track of, I'm this far away, so what is the new angle? We don't have to worry about that. So, and in the lab, actually, I was looking at last year's results, incredible. R squared value of 0.9994, I think it was. Now the other part of the lab is, this is all well and good. We have the sensor here with pointing straight at the light source, the middle of the light source ideally. But what happens if we started rotating our sensor?
To like say the side of the side light source, or?
Yeah, or as in, I got my source right here, and I have a surface like that, straight on. If I tilt my surface like that.
Would you do something similar like you did with the, when we did the spring and you had, find the average of the two, find the top, find the bottom?
No,
and
no.
the average?
No, because if you kept this in the same spot, you would get the same value, but in reality, you don't. If light's coming at it at an angle, you actually need to do a component, a little bit of trig.
Well, if you spin that as a sensor, it's only gonna get slight of that light.
Right, and so we need to take that into account. So if we think about the light coming in at that angle right there, and the surface here pointing in that direction, this would be known as an area vector. The area vector is perpendicular to the surface, so if I deal with an area vector of the top of this table, the area vector would be pointing upwards. The magnitude is the actual area, but the direction is perpendicular to it. So if we tilt this at an angle, that area vector starts changing with it. It's always just going perpendicular to the surface as the surface changes. We need to know that angle right there. The angle between the light, as it's coming straight in, and the perpendicular, the normal is the better term, the normal to the surface. The farther we get away from that, the more perpendicular it becomes, the less,
Right.
yeah, the less it's hitting. And so, well, the trig function that is maximized when they're together and minimized when they're perpendicular is, what trig function is the maximum value when the angle is 0 degrees and 0 when it's 90 degrees?
Fine.
Or the other one,
Cosine.
that's the one. And so we have a cosine feature brought into this. And so what I would expect to see is that the luminous intensity is proportional to the cosine of the angle. Now this is a trickier one to actually perform in the lab, because you gotta pick the right pivot point. You'll have the light bulb, you'll have the sensor straight on at some set distance, and you need to keep that same distance. You don't want to move it back or forward, at least the sensor part back or forward, because that's going to change it, as we just showed right there. And if we pivot about that point, well, then it's going to start moving away. We need to pivot about this point right here, smack dab in the middle, so so as you move it, you're basically swinging the rest of the sensor around that middle point. And so it's trickier to execute, but it is doable.
So the radius in this case would be the distance from the light to the sensor.
Yes.
And the area would be the sensor part.
Yeah, the area of the sensor itself.
Have you posted a lab yet, or?
Yeah, it's posted.
Okay.
Should be.
I thought it was
It is,
today,
I'm
so
sure.
I turned it in.
Okay. So I guess it is posted.
It is, I wanna make sure, for some reason I was thinking it was today when I thought it was for tomorrow, I went, good, I'll have to try to print it out.
Yeah, I thought it was today too.
Trying to think of, do we have time to do it today?
No, I don't have my lab.
Well, we may not have time to do it tomorrow.
Yeah, the other tricky thing that's gonna be for the lab is light source. We can bring the shades down, and I mean, there's obvious ambient light. One of the issues I remember last year's group doing this, when they were measuring ambient light, it mattered the direction they were pointing it in, because the little bit of light that was coming in was bouncing off the bits of metal and then hitting the sensor. So,
It is supposed to rain tomorrow, if that makes it any better or worse.
it might make it a little bit better, but I think we probably we'll have to we'll worry about it when we get there. And then, if I have two groups, the light from each group could be interfering with the other group. So,
Well, I thought we may not even have time tomorrow. We only have a quiz tomorrow?
yeah, but we got 2 hours. How long do you think the quiz will take?
I don't know.
And I think I'm done with 33. Anything I missed? Yep, got it all. And now, any questions before I jump on ahead into 34? Back to 34, I should say.
I have a question, but it doesn't have anything to do with this. I
Okay.
was thinking about it after you, for some reason it came to me in the middle of the lecture. For the numbers for Calvin, on one sheet it says, I think in the book it says 273, and on the lab sheet, you have 273.15, which would you prefer us to use under most circumstances?
For a lab, 273.15,
Okay.
because going for the greater precision, 273 is rounded off, 273.15 is actually the official number.
Well, let me ask you this, if for some reason in, let's say, quiz, homework problems, master set, anything like that, doesn't matter,
I'm less concerned there.
okay. So either one of them could be used,
Correct.
okay.
Yeah.
Unless it's given in the problem.
Yeah, that's true.
Yeah.
But if we're having to pull it out, then either one's acceptable, unless it's
Yeah.
given.
I mean, it's a question of, if your answer is correct, I'm probably not even gonna notice which one you used. Get your question answered?
Yes.
Okay, other questions?
Are we gonna get any of our other labs and quizzes and
Oh.
stuff back?
Yeah, that would be a splendid idea. I just have to remember what I did with them. I had stuff to return yesterday. I didn't return anything yesterday, did I?
No. Probably in your office.
There's that task to try to get stuff graded, and then once I have it graded, I think, oh yeah, done it. And then I forget the last part. I'm gonna set the alarm, see, we're done at 10 till.
Yes.
I'm gonna set the alarm for 20 till to give me a chance to go get that stuff, assuming my phone doesn't die. The coin illusion, you were talking about what would it look like if the image were in front of it? The note I have here is clamshell mirror floating coin illusion. Clamshell mirror floating coin illusion. And I'm assuming I wrote that because that was the key phrase that I saw for actually finding it. Get a hit on that, or are you still typing?
I'm so glad.
Don't feel it. That's fine.
I think I found it.
Okay. Oh, that's right. All right, let's take a look at a couple other situations with mirrors. We're gonna do a convex mirror.
And this is back to 34, right?
Yes, it is. Thank you for handling the transition. Convex mirror with radius of curvature of 20 centimeters. Object is 30 meters, 30 centimeters in front of it. Images, I'm just gonna leave it generic like that. The book goes in specifically in what is the nature, size, position, etc. We're gonna find everything we can about the image. All right, so first off, what is the focal length? What is F?
30 centimeters.
No. The number is not written on the board, but you can find it from a number written on the board.
Yeah.
15?
Is it, yeah,
Not 15.
10?
Why?
It's half.
So it's half the radius of curvature. Now, there's one other twist here the fact that it's a convex mirror and all the stuff we did yesterday was a concave mirror.
It says it's gonna be negative, right?
Yep, negative 10 centimeters. You get a very different answer if you have positive 10. So let's just do the math bit first, and then we'll look at the rays. So I got 1 over P plus 1 over Q is 1 over F. So 1 over 30 plus 1 over Q is equal to 1 over negative 10. So do the math thing. So I guess 1 over Q is negative 1/10 minus 1/30.
3 is 2 30ths, so that'd be 1/15 negative. No, positive.
Okay, that's negative 3/30 minus
That's
1/30, so it's negative 4/30. So we end up with Q being negative 7.5. You got 2 negatives there.
Okay, turn positive.
It doesn't, we're not multiplying, it doesn't turn positive.
Well, you got 2 negatives, so you add it together.
Yeah. All right. So in terms of the ray diagram, I got my central axis there. I got my mirror. We're gonna make that 10 centimeters there, so 10. I guess that's my radius of curvature would be right there. That's my center. This is my focal point. So my object is here. Now when light comes in, if light coming in straight is gonna hit the mirror, it's gonna bounce away from the central axis. Unlike with the concave mirror, it's gonna hit and head towards the axis. Here it's gonna hit and move away from the axis. So the light's coming in, boom, and it hits. Now before, if light coming in straight would bounce towards the focal point, this time it's gonna go away from the focal point. So sort of a virtual right there, and the light's gonna bounce off like that. Light that comes in towards the center will bounce just like before. But the image is going to happen where the light rays seem to meet. And so we sort of backtrack here. A little bit better. Because if your eye is over here, your eye is going to be getting these light rays coming into it, and it's going to process it. It's going to sort of trace back to where it sees an image by working backwards. And so the image will be here. It is a virtual image because the light rays don't actually meet where the image is. And something that's going to be true for lenses and for mirrors, the fact that Q is negative is telling us a big clue there that we're dealing with a virtual image. The magnification, that formula still holds. Magnification is negative Q over P. So that becomes negative 7.5 divided by 30. Which is 1/4. So my image is going to be 1/4 the size of my original. And because my magnification is positive, it is pointed in the same direction as the object. So we know magnification, we know position, and we know the nature of it, the fact that it's virtual and upwards. I think.
And you said if it's positive, it means it's pointing towards the object.
It's pointing in the same direction as the object. So, because the object's pointing up, the image is pointing up.
So for it to be a real image, it would have to reflect back to the object.
To be a real image, it would have to be, for a mirror, it'd have to be on the same side as the mirror. Because the light rays have to meet, and the light rays are not penetrating the mirror.
Mhm.
It just appears to be.
So if it was a concave mirror and it went back to the object, it would be a real image?
Yes. When you say back to the object, that's the part I'm getting hung up on.
Yeah, when it reflects off of the mirror, back to the object, or back to the image, sorry.
If the light rays actually do meet, then yes, it's a real image.
Okay.
Which only happens if they meet and then come towards each other.
But it doesn't have to necessarily be at the object.
No,
Okay.
no, they're not, I mean, yesterday we did examples where they didn't meet at the object.
Right.
And since we're here, in a different color here, so let's work it around, same problem, except this time concave mirror. This is what we're working with. Plug and chug, so we get, well, the only thing that's different between this and the previous problem, in terms of the math, is the focal length is positive now. And then, sorry,
No, sorry.
so then 1/q would be 1/10 minus 1/30. And we get 1/15, and this is what Ronald was doing. So q is 15 centimeters. What's the magnification gonna be?